We have already seen how to work with mixed effect model, and the general form of the mixed effects model that we have seen is this: y equal to x beta plus zg plus epsilon, with suitable assumptions on the random parts g and epsilon. I have also hinted that it is possible to have a model in this form which is of no practical value, which has no real life interpretation. One example that I have mentioned is this: yi is equal to alpha naught plus alpha 1 xi a2 xi squared then alpha 3 xi cubed. That is, I am fitting a cubic polynomial, but out of blue I am just making a2 a random coefficient. It is impossible to come up with any real life situation where this will be the natural model. However, it is still in that form. So anything that is of this form need not be meaningful. In order to avoid creating meaningless models, we have given one way, and that was think in terms of the box diagram. Look at the inputs, identify the input which is not going to be important, or the particular levels of which are not going to be important in future. Consider that as the random input. Then if that involves subscript say j, everything involving that subscript j, all the coefficients with that subscript, will be considered as random effects coefficient. That is how R also wants you to think. So you can think of all the models that we can couch in this particular form as one set. So this big set, it's like a Venn diagram. This set is the set of all models of this form, and all the models that come from this particular way of thinking is a subset of that. It's a rather small subset. So there are other things out here, many of which are just meaningless. However, there are certain types of models which are somewhere here. Those are actually meaningful. Now we are going to discuss three such types of random effects model or mixed effects models which are not of this type outside this set, however, which are of this type, and still these are meaningful models. The first type is where we have a model like this. I have got mu plus alpha I plus beta j plus ai plus epsilon ij. The striking part here is that I have the input denoted by I as the fixed effect as well as the random effect. So this might look surprising. How can the same thing be both fixed and random simultaneously? Actually, this is a very simple trick to incorporate non-zero mean. So when we say that AI is a random effect, we have some such assumption in mind. AI follows normal 0 sigma a square. Now by the theory of linear mixed effects model, we always make the mean 0. But it may happen that you actually expect this mean to be non-zero. So AI will have some non-zero mean which you do not know. So the mean of A1 need not be same as mean of A2. That mean is just written separately out here. So this is basically same as the model. You forget about alpha I here and you put the alpha I here. So you are having AI's random effect, normal, mean some unknown alpha I and variance of sigma a square. But since standard softwares will always put this assumption, it has to be 0, you just make that into a separate fixed effect. So that is why you sometimes see in a linear mixed effects model, the same thing is listed both in fixed as well as in random. Now the effect here is that this is the design matrix X, mu's, the alpha columns and the beta columns. So I am assuming I goes from 1 to 2 and j goes from 1 to 3. Then the z, which is just ai, is nothing but the two columns of x devoted to the alpha i's. So z is actually a submatrix of x. This is actually a very common situation where all the columns of z also occur as columns in x whenever you need non-zero means of the random effects. Now if you want to express this model in R using the function LME, then here is the syntax. You write fixed equal to y tilde I plus j. I am using the same name for both the variable as well as the subscript. I plus j, 1 is implied, and the random is tilde 1 given I. That is for the alpha, for the ai term.